Hello, 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 if you can hear me. Hello, hi, hi, okay. Hi, Kirsten, thank you. Hello, hi, Miriam, thank you. Hello, Kay. Oh, I see. Hello, Olsmail. Hello, Sarah. Hello, Katya. Hello, Abdel. Hello, Tobias Santa Galloway. Hello, Ashley. Okay, hello, bro. Excuse me. Hello. Oh, wow. All right. It's all happening. It's all happening. Wait, so I'm going out of order here, but did I say Katya? Okay. Osmail, Abdel, Sarah, Katya, Kay, Ashley, Tobias, awesome. Mariam, Kirsten, Osmail, Montserrat, Tobias, Kay. Oh, what's up? Yeah, what's up with you? Good question. Thank you. Not much. Brian, yes. Sarah, yes. Hi, Alejandro, and hi, Jasmine. All right. I think that if I double said your name, it's because I'm seeing you in the chat and on video. Okay, yes. Hello, hello. Okay, great to see you all. Oh, wait, there's more people. We're gonna get rolling. Top of the afternoon, yes. Top of the afternoon. Okay, this is awesome. All right, so we're getting toward. I'm going to dive in. So, oh, and yes, hello from 2D. All right, awesome. Or hello from 3D. Awesome, awesome. And yes, all right, I'm just going to get rolling here. But again, I want to repeat, it's been such a pleasure getting to know an increasing number of you in the hallowed halls of 3D. It means a lot. I appreciate it. And there's still many of you that and it's not a thing about, anyway, over time, hopefully I'm going to get to know all of you one way or another. And hopefully I'm going to see you in 204 and blah, blah, blah. Good afternoon, Jose. Yes, thank you. Oh, and there's more people coming. Okay. But I just wanted to, so I'm about to say some things that are of logistical importance, and then the rest is physics importance. Anything I'm about to say in terms of like time and space details of the rest of the semester, I will also put in Google Classroom, to be explicit, but but here's the plan, or here's the deal. I hopefully by 8 p.m. or so tomorrow night, I will post a practice document for your final exam, which we're going to talk about for the rest of today and on Monday. Ideally, it'll be posted around 8 p.m. tomorrow. If I fail, then it'll be posted the next day. But you'll have a practice document, which will be basically the rough draft of your final exam, that you can look at and do whatever you want with over the weekend. Sorry. Oh, you have, okay, is that true? Oh, hold on 1 second, hold on. One second. Things are happening in the direct chat and okay. Okay, so sorry, I'm just responding to a couple of things at the same time. Let me back up. So you have class today. We have class today. We have a final class Monday of next week. Approximately Wednesday of next week, Wednesday the 14th, I will post your final exam, which, okay, thank you, direct chat person. Thank you for understanding. Thank you. I will post your final exam, which is not cumulative, like it doesn't explicitly cover material from before the last test. It is also hopefully going to be shorter than the last test. It will cover this material that we've been doing right now, The final exam that will be posted a week from today will, be extraordinarily similar to the practice document that you'll get in advance, tomorrow, or at worst Friday. I'm going to give you an overview of what's on it in like 2 minutes. But then you'll have till the file, so it'll be posted a week from today. Again, you may want to jot this down. I'm going to put this in Google Classroom, but I just want you to know so that you can prepare. So it'll be posted a week from today, and then you'll have to the following Monday. Is that right? Which is like the 19th to do it. Okay. Again, take home, open universe, all the same routines as last time. So that's the story. And as to what's on it, okay. Okay, but I can't untangle it in time for as to what's on it, that's what we're going to talk about right now. And everything that we say for this period, this class period, and the Monday class period is all relevant to or necessary for the final exam. That's all we're going to talk about for the next 2 periods. One thing to warn you or to be clear about, there will be nothing on the final exam that isn't in the practice document. There will be no surprises or anything like that in the final exam. The practice document will make it clear what's on it. You will see some things on the practice document that we're not finished with until the very last minute, until Monday. There are a couple of final equations that I want to give you today and Monday that you'll see in the practice document. Any new equations that I'm giving you as of today or Monday, you're going to be tested on in a very low level, straightforward, like plug and chug kind of way. I'm not going to get all elaborate or crazy with any new equations or too deep, but there's a couple equations I just want to make sure that you're familiar with before you go into Physics 204, and they will be introduced today, and you'll see them in the practice document. So again, so you may see things tomorrow in the practice document that you think, oh, this is kind of new. What is this? And any loose ends that I have to tie up, I will tie up on Monday. But you won't see anything on the final exam that you don't see in the practice document. That's the bottom line. So wait, let me see. I'm looking at the chat. Posted Wednesday the 14th. Yes, that's correct. Thank you. Yes, thank you. And again, I will confirm that, or I'll repeat that in writing in the Google Classroom. But yes, what Ashley has put in the chat, that the final exam will be posted Wednesday the 14th and due back Monday the 19th. Again, so you take it home, you don't do it under time conditions, but cool. Thank you, Ashley. Awesome. Okay. And again, until Monday, the last class, anything that you want to still find that you want to catch up and turn in for points, please do. Even if you don't see the points yet, it's just points that do get added and do get included in your final average, I promise. And anything that I still owe to you, apparently there are still, I thought I was done, but apparently I'm not. There still are some documents, some exams that I've got to get to some of you. I'm so sorry. I thought I was done actually, but I think I'm wrong. So we're still catching up with each other. In effect, from here on in, news should only get better for most of you. I will also say, because I've taken a while with these midterms, something I've done in the past. Okay, I'll say this quickly. Wait, should I say this? Yeah, especially for those of you who are still worried, either because of a number you did see or a number you didn't see yet. Right, you could still turn in that problem for the extra 8 points, and I hope you do. Right, today's Wednesday. Right, you could still turn that in. Please do. Anything that's old, you could still turn in for points. The only thing, so 2 quick things. One, the only thing I don't want for you to turn in between now and next Monday, like the one thing I don't want is a lot of old game turns, like the nightly or daily game turns, the 5-point things where you just say what you did in class that day. Don't turn in old ones of those, it's sort of pointless and confusing and strange to do that at this point. But anything else, even including those game assignments that it did say that they were due December 1st, but I just meant that to mean the end of the semester. Those like avatar, video, YouTube, any of those you could still turn in, and please do, for points. Anything that applies, feel free. And any old homeworks, feel free. Just the one thing I will, and believe me, and I still owe you points, and you'll get them. But just the only thing I don't want is old game turns. That just sort of doesn't make sense at this point. So that's number one. Number two, let me just assure you all too, and because I know I've taken a while with things, and I know how hard you all work and all of that stuff. I want you to understand that the final exam is meant to be another opportunity to practice physics, to improve your understanding, and to improve your grade. It's not meant to be something that can all of a sudden throw somebody off the beam that feels like they're okay. What am I saying? I'm saying this, that one thing I've done in the past that I will probably do this semester, well, I will definitely do it. And I will do it to how explicitly I do it, I have to figure out, but that I will put more weight on whichever of your two exams you do better on. Like how much more I still have to decide, how explicitly I do that, I still have to decide. But I'm telling you all right now that if you did badly or worse than you want on the midterm exam, or for whatever reason you still haven't gotten it back yet, and so that's really worrying you, I want you to know right now that if you do better on the final exam will count a little bit more in your average. Conversely, if you rocked the midterm, I still want you to study, and you still have to take the final exam. Like I don't drop a grade because there aren't enough grades to do that. I never drop an exam grade. But if you did well on the midterm and you feel like things are going well for you, yes, you still have to study and take the final exam, but don't go into it worried that all of a sudden you could blow up your whole situation by accidentally having a bad day on the final exam. For all of you, I'm saying one way or the other, I will put more weight on the thing that you did better. I can tell you that. Exactly how much I can't tell you. Exactly how I do that, I can't tell you. But I can tell you all that in general, what you're always looking for in this class and in Physics 204, you're looking to give me your best work somewhere or other at some time. And you're looking to believe and trust that it's your best work that makes the strongest impression on me and helps your overall average the most. Your best pulls up the rest. Honestly, there's karmic ways in which that's true, but there are also strict mathematical ways in which that's true. Okay, so just know that. All right. Okay, now I'm gonna start talking about the final exam now. Okay, and the rest of everything I say is about the final exam. So, I'm switching the boards. Okay. Oh, and of course, Zoom just stopped. Of course, the board just. Hold on, the board's gonna have to come back. It happens every time. I don't understand. Hold on. It's coming. I don't understand why. Okay, here it comes. Okay. So I'm going to tell you about all the problems on the final exam right now, okay? I'm giving you an overview. You're going to see them explicitly in the practice, but I want to focus your thoughts. And I'm saying like one problem. I'm not telling you if it's problem number one or problem number two or whatever. And there might be even choices. I'm not getting into all that right now. But one problem on the exam will be very directly related to everything we've been saying in class the last 3 days, very directly related to lab number 5, okay? What it's going to ask you to explicitly do is build up the system schemas, the pure free body diagrams, the action-reaction pairs, the choice of coordinate system, and the component free body diagrams for a mass on a rough inclined plane, again, like lab 5. And what the goal of this one problem is going to be to do enough work to see and show me how you can calculate the acceleration up a rough inclined plane and compare that to the acceleration down a rough inclined plane. Okay, maybe there will be numbers, probably not. Whether there are numbers or letters like M and G and mu and so forth is, again, very much like what was happening in lab 5. And the idea behind this problem, and I'm going to be more concrete when I turn the page in a moment, like I'm going to show you the equation, to some extent, the equations I'm talking about, but most of the diagrams and the buildup and the derivation of those equations we've been doing in class together for the last 3 days. So I'm talking about those class notes, like the last 3 days. But I want to give you, but I'm going to tell you, like in the problem, you need to know the trees, the details, the mathematical details that we've been doing, but I want you to see the big picture of the forest as well. So the big picture is what I'm talking about right now. When you walked into that lab weeks and weeks ago, lab number 5, and you were told that you were going to flick some object up a rough inclined plane and it was going to go up for a while and then run out of steam and then naturally come back down to the bottom of the plane. And you were asked, I believe, you were asked to predict whether you thought the up trip would take the same amount of time or take more time or take less time as the down trip, right? And then you made a prediction, and then you took a bunch of data and you found out what actually happened, and then you did a bunch of analysis, and it like went on for a long time. Let's step back and say, I would imagine that what you eventually found in that lab was perhaps a little different from what many of us did or would have predicted. To be clear, if I were a normal person, I mean, yeah, if I were a normal person, without much physics study, if someone asked me about an object going up an inclined plane and then coming back down, my basic instinct would be, well, if anything, I assume it's going to take more time to go up and less time to come down. I mean, it's harder to go up things than it is to come down things. If I were just like thinking with my gut, I would say, I would imagine that something going up would take more time than something coming down. And I don't think that would be a crazy or stupid thing to say. I think it'd be a natural, common thing to say. Let's start with that. Like me, if I were to make that prediction. And I think it's important to remember that, like the intuitive, reasonable, common, not crazy thing to think about an up-down trip on a rough inclined plane would be, I would imagine, long time, short time, right? I'm not saying that's right, but I'm saying that that would be a common prediction that I think is important to remember before we go any further. I'll also admit now that if I had some physics exposure, if I had taken a physics class or two, or I was in the middle of struggling through a physics class, if I had gotten used to some ideas of physics, and if I had gotten used to the idea that sometimes in physics things are surprising or not my first instinct or whatever, and if I had even gotten used to the idea that in physics, like if you throw something up and it goes up in air, in free fall, and then it comes straight back down, like in the first exam that we took, if I had gotten used to that idea and the idea that sometimes physics is surprising, I might think, well, when you throw something up, the downward acceleration due to gravity, the constant acceleration due to free fall gravity is like 9.8 meters per second squared or 10 meters per second squared or whatever. And even when it's coming back down, it's still 9.8 meters per second squared or 10 meters per second squared. That is, the rate at which it loses speed on the way up is the same as the rate at which it gains speed on the way back down. So I might say, with a little bit of physics experience or a little bit of, with a little bit of physics experience, I might say, well, I'm getting used to physics now. So if you flick something up an inclined plane and let it come back down, I imagine the standard physics response is it's probably going to take the same amount of time, because after all, it's the same gravity on the way up as it is on the way down. And even though it's losing speed on the way up and gaining speed on the way down, it's probably doing that at the same rate. So I would say it's probably the same time. I might eat, and I'm not saying that's right, but I'm saying that would be a very reasonable thing to think. And in fact, would show that I had learned some physics. I might even go further and say, well, okay, there's friction on this inclined plane in this lab. It's a rough inclined plane. So there's friction, but I assume the friction is the same amount on the way up as it is on the way back down. So I assume the argument would apply to friction just the same way it did to gravity. Same forces on the way up as on the way down. So I might say up should equal down. Now, I'm not saying any of that to confuse you. I am not intending to confuse anybody. I am intending to be very expansive and as clear as possible on something that actually is confusing. I'm here to say explicitly that what we found out in the lab, what we found out in lab 5, is that if you send something up an inclined plane, a rough inclined plane, and then let it come back down, even in the real world of a regular lab with regular everyday objects, as long as you're somewhat careful and somewhat controlled about what you're doing, what you find is that if you send something up and then let it come back down, it takes less time to go up and more time to come down, right? Like, let's be super clear now. What you actually found, I mean, I don't know if everybody did it perfectly, but if you did it reasonably in the real world of your actual real lab, what I believe most of you ultimately found out is that you sent something up a rough inclined plane and let it come back down. Now, all naturally, it goes up quickly and it comes down slowly. In fact, the lab is called slow down, right? It goes up quickly. It takes less time to go up and more time to come down. Now, I want to pause on that because that's like the right answer. Like, that is what you found, I think, or should have found in lab 5. And I want to pause on that. That's the right answer. And I'm going to tell you right now that one of the problems on the final exam is I want you to show through diagrams and equation and vector component manipulations and equations and words. I want you to be able to show why that actually is true, why it actually makes sense. And I'm going to tell you right now that the best way to make sense of that and show that it's actually true that things take more time to go up than they do to come down, at least when they're on rough inclined planes. The best way to be able to nail this problem on the final exam, the best way to be able to actually use physics to show why it does make sense and is true that an object sent on a round trip on a rough inclined plane will actually take less time to go up and more time to go down. One of the key ways to be able to make sense out of that and show it is to first be honest in your mind and first acknowledge that that is a surprise. Okay, all the stuff I just said for 5 minutes, a minute ago, when I was saying what I would predict if I weren't a physics student, and then what I would predict even if I were a physics student, I was not, this could be confusing to some people, especially in a Zoom class. I'm not saying all that stuff to throw you off. I'm saying that if you really want to understand the right answer to this physics problem, the first thing is you got to acknowledge that it actually is a surprise to most of us. I don't think it's what we would expect. If everything I'm saying about up is fast and down is slow, if everything you hear the whole time is just like, yeah, duh, I get it, yeah, duh, then I'm warning you, I don't think you're listening hard enough. Like, I'm not saying, like the way to get this point is to see that it actually is a big point. Quick sidebar. One of my questions in physics for all time, for all of you in any class you take, physics is at its best when it shows us things that we didn't expect, but that we ultimately see make total sense, right? Why are black holes and big bangs and those kind of things exciting to people? They're exciting because they're unexpected, but that ultimately we can't argue them. They ultimately actually seem to make logical sense once we think it through. Otherwise, we wouldn't believe, right? But they are a surprise at first. Well, the rough inclined plane is like that. And other problems that we've done in this class so far, it is a surprise. In order to actually make sense of it, you got to first acknowledge it's not obvious that something would take more time to go down than it would to go up. Okay, but now what? But it does. So why? Why is, if you do all the diagrams that we've been doing for the last 3 days, the system schema, then the pure free body diagram, and then you choose your coordinate axes appropriately, if you tilt your coordinate axes to line the x-axis up with the inclined plane itself with the direction of acceleration, and then you divide mg into mg sine theta and mg cosine theta, like we did yesterday, like we did the day before, and you do F net equals MA in the x-axis and separately in the y-axis, what you ultimately find, so here I am, I'm like skipping a lot of steps. They're all in your class notes from the last few days. But what you ultimately find, what we found yesterday, is that the acceleration while going down the plane is g sine theta minus mu g cosine theta. Whereas the acceleration going up the plane, the acceleration while the thing is going up the plane, is g sine theta plus mu g cosine theta. Very important distinction. Now, again, to be clear, what we got as far as the down statement at the end of last class, I'm telling you now that if you look at your diagrams, if you draw all the diagrams, you'll see that the one difference between traveling up versus traveling down, the one difference is that friction flips the friction arrow, and the friction arrow happens to be mu times mg cosine theta. We got that because friction is mu times the normal, and we found out looking at the other axis that the normal is equal to mg cosine theta. So the friction force is mu times mg cosine theta. When we're traveling down, it's pointing up. When we're traveling up, it's pointing down. It's the only thing that changes from one diagram to the other. Gravity does not change. It's always pointing down. This change makes all the difference in the world. Like the value, so the value of the gravity component is always one number that never changes. The value of the friction component is always one number that never changes. But when you are traveling, let me start with this. When you're traveling up, it is true that all the forces are against you. When you are that block traveling up the inclined plane, the friction and the gravity component are both working down. So they seem to be working against you, which is why everybody intuitively thinks, oh, well, I guess I'm going to have a really hard time getting up. Like all the forces are against me. I guess it's going to be really difficult. I guess I'll probably take a long time to get up. But here's what I'm here to say. And here's what I want you to understand. When you're traveling up, the two forces are working together. They're working together. They may be working against your direction of motion, but they're working together. Say the gravity force is like 3 newtons, and say the friction force is, say the gravity force is 4 newtons, and say the friction force is 3 newtons. I'm just making up numbers, right? Then those two forces are working together. They're adding together to make a net force of like 7 newtons. So when you are traveling up the plane, there's this huge net force working against you of like 7 newtons. Now so it makes a huge magnitude of acceleration. F net equals ma. So when the F net is huge, the acceleration is huge when you're on your way up. Now you might say, yeah, but wait, but I'm on my way up, and like all the forces are pointing down. So the acceleration is pointing down, right? So isn't the acceleration like in the wrong direction? Yes. Yeah. Oops, someone's here. Sorry, hold on one second. Yes, correct. And again, please, if you could be taking notes on what I'm saying at all right now, please do. In fact, sidebar, one thing I've been meaning to tell you people, one thing that made a difference in some people's midterms versus others is any of you who ever knows how to take the things that I say that I can't write down or I don't write down are often the difference in actually understanding this material versus just spitting back equations. Like if at all you can be taking notes on what I'm saying right now, I highly advise it, because you're going to see when you see the practice exam, I'm going to try to test to see whether you actually understand conceptually how it could make sense that an object would take less time to go up than it would to come down. And that's what I'm trying to explain in words right now. I promise you, this is not a digression. We're not like off the topic now. Like this is the topic, just okay, even though I'm not writing it. So what I'm trying to explain for anybody who might have just tuned in is on that last term on the page, A up equals G sine theta plus mu G cosine theta. And again, you would have derived that. Like you're going to go through steps in a problem to show why that thing is true. And those are the steps we did in class notes the last 3 days. But once you get that statement, A up equals G sine theta plus mu G cosine theta, what I'm saying in English about it is, okay, let's say gravity was pushing against you with like 4 newtons, and say the friction was pushing against you with like, say 3 newtons. So they add together, and now there's this big force of 7 newtons. So it makes this big magnitude of acceleration. Now, the big acceleration is a negative number. Oh, yes. Like you're going up. Like, let's assume that down is negative. Oh, yes. It's a negative acceleration. What does that mean in English? It means you're slowing down. For sure. You're slowing down. Yes. But apparently you're slowing down at a really, really high rate. And when are you going to get to the top? When are you going to get to the top? You're going to get to what is the top? The top is wherever you run out of speed, right? The ball isn't trying to get to some particular destination in geography. The ball is just or the block, whatever, the object is just sliding until it runs out of speed, velocity. So on your way up, you've got this huge net force working against you, this huge net force producing a huge magnitude of acceleration, meaning a huge rate at which you are losing speed. So you say you start with 15 meters per second of initial velocity. You're losing it really rapidly. So you're losing a lot of units of speed, like a lot of meters per second every second. So in very short amount of time, you hit zero, you've run out of speed, you're at the top now, you start coming down. Now, so you get up quickly because you lose speed at a very rapid rate. And you get to the top once you've lost all your speed. So now you're at the top. Now you start coming down. Now friction flips its direction. Friction's still the same magnitude as it always was. Gravity is still the same magnitude as it always was. But now friction and gravity are in conflict with each other. Granted, gravity is helping you down now. So people tend to think intuitively, well, now gravity's helping me. It's got to be easier to come down now. But look, now on your way down, friction is not helping gravity. Gravity may be helping you, so to speak, but it's not helping friction. Gravity and friction are now in conflict when you're on the way down. Say that gravity force was like 4 newtons. Say that friction force was like 3 newtons, like we said a minute ago. Now they're in conflict with each other. Like look at the statement at the bottom of the page. A down equals G sine theta minus mu G cosine theta. So now it's like 4 newtons minus 3 newtons, 1 newton. Much smaller net force on you on the way down. Not because any fact has changed. The only thing that's changed is the direction of friction. But that now means that friction and gravity are not helping each other anymore. They're in conflict. So now you have this small net force on you on the way down, F net equals ma. So you have a small magnitude of acceleration on the way down. Like it's not the same. This is not like throwing something up in the air and it comes back down. It's not like 9.8 up, 9.8 down. This is now like, God knows, like 4.9 on the way up magnitude and like, I don't know, 3.1 or something, making up numbers on the way down. Now on the way down, for sure, that acceleration, oh yes, it is in the same direction as your travels. Oh yes, it seems to be helping you. Like on the way down, you are speeding up. For sure, you're speeding up on the way down, but you're not speeding up on the way down at the same rate that you were slowing down on the way up. So on the way up, you lost velocity at a super rapid rate and got to zero super quickly. Now you've got zero velocity. You're trying to gain back your velocity on the way back down. You're gaining back, but you're gaining back at a much smaller rate. So by the time you get to the bottom, you don't get back all your velocity. You just don't on the friction inclined plane. If you went from 15 meters per second of velocity to zero on the way up, then on the way down, you're going to go from zero to something smaller than 15. I don't know, something like 12, right? Because you're gaining back at a lesser rate than you were losing in the first place. So you, on your way back down, you only get back to like, I don't know, 12 meters per second of velocity. So your average velocity on the way down is only like 6 or something, whereas on the way up, it was like 7.5 or something. So on the way back down, on average, you go slower, and therefore you take more time on the way back down. Definitely a surprise, but undeniable once you think it through and you draw all the diagrams, you draw the forces. It's not an accident. It has to be that way once you think it through. One of the big, and that's what I'm going to ask you. I'm going to move on in a moment. I mean, but obviously, please put any questions or anything in the chat, please. But I'm saying one of the problems, I'm going to ask you to draw the diagrams like you've been doing. I'm going to ask you to choose the tilted coordinate system, because it's like easier to see this in that. I'm going to ask you to walk through, do the forces, do F net equals ma, and show how the accelerations compare up to down. And then you're going to be asked somehow in English to explain, or maybe to put in numbers. I'm not sure if there'll be numbers or not, but somehow you're going to show me that you get why it actually makes sense that you would take more time to come back down than to go back up. And ultimately, this means you have to understand forces and all of that. But also one kind of hidden lesson in all of this is there's a big difference between speed and acceleration. There's a big difference between speeding up and having speed. Going down, you are speeding up, but that doesn't mean on average that you have more speed than you did on the way up. This is all like the difference between acceleration and velocity, if you think about it. But anyway, so that's going to be one question, is to show that. Okay, wait, I'm just going to pause for a second. We still have time. We've got a half hour. Okay, that's one of the questions on the final exam. That's not the exact question, but that's what you want to prepare for, practice, or get ready for, or know. And it's all in your class notes from the last like 3 days. Can I just get a show of hands if you, even if you don't understand them, like, do you understand that that's what I'm saying? Like, are you clear with me that I'm saying that's part of your final exam? Oh, thank you, Katya. I just saw that, Katya. Thank you. Okay, it's good enough for me. But is Katya the only one? All right, well, Katya's the, no. Wait, can anybody else show me a show of hands? Is that clear? That's one of the questions on the final exam. Okay, cool. Thank you. I think that was my, thank you, Tobias. Okay, thank you. Oh, 4 people. Okay, thank you. Oh, thank you, Katya. Thank you, Kay. Thank you. All right, cool. All right. So that's one of the questions. Again, you'll see the exact form tomorrow or whenever, but then the next question, very related, but different. Very related, but different, like a different thread on the, and there goes my board again. I'll tell you right now while I get the board back, golly. You should put a question on my final exam, like, how do you use technology? Yeah, the answer is not well. Hold on, I'm just wait. Sorry. So another question is also about the final. Is also about the inclined plane, because there's a lot going on in the inclined plane, and we spent a long time on it. So another question. Yeah, here it is. Okay. This question is also about the inclined plane, but there won't be friction on this one. On this one, I'm going to ask you to set up a smooth inclined plane, like mass, angle theta, but this time with no friction. And you're going to be asked to solve for the acceleration of a block on a smooth inclined plane without friction. But this time, I'm going to ask you to directly walk through the solution for 2 different coordinate systems and show me how whichever coordinate system you use, you're still ultimately going to get the same answer in the end. It's going to be different mathematical process, different solution work, but same answer. And you'll even know the answer in advance. It won't be a mystery. So these are problems that it's not going to be a big mystery what the answer is, but they're kind of like proofs or demonstrations. You want to practice this. You're trying to explain and show things to me. It's not a matter of, do you know the answer? It's a matter of, can you show why the answer is the answer? So on this one, and they're both, notice, sort of compare, contrast kind of things. The first one is compare the up situation to the down situation and really show where is the difference that makes a difference. And this one is show one coordinate system versus the other and show the difference that makes a difference. I'll be more specific. And this also we've been talking about for the last 3 days. So here's the situation. Again, we have like a mass on an inclined plane. The mass is given as mass m. We're at the surface of the Earth, where we assume that free fall acceleration due to gravity is g. And here again, you're going to be solving for the acceleration of the mass on the inclined plane. Only this time there's no friction. Okay, and you'll look in blue. I'm saying in blue, whatever you do, I'm telling you right now, the answer is going to be that A equals G times sine of theta. Right, and notice that there's not numbers here necessarily. We could test in the end to see if our answers make sense by testing particular numerical values, but we don't need numbers to ask this question. One thing I want you to notice and know is no matter how you slice it, if you have a block on an inclined plane, if you have an object sliding down a slide, it accelerates at a rate that is sine of the angle times g. Now, first of all, before I go any further, I want to make sure that makes sense to everybody. I mean, you've seen it now a bunch of times in lab and stuff, but hopefully you see that that makes sense. Like, remember, I mean, G is that number, 9.8 meters per second squared. G is how fast things would accelerate if they fell straight down. Sine of an angle is always some number between 0 and 1, right? I mean, if the angle is an acute angle in the first quadrant, the sine of the angle is always some number between 0 and 1. In other words, there's always some fraction. Think of fractions as just like percentages. Like, think of or some decimal. Think of like the decimal 0.67 as meaning like 67%. Then if we say that the acceleration down an inclined plane is g times the sine of the angle of that plane, what we're saying is that things will slide down a plane at some percentage of the free fall number. And we're saying the steeper the plane, the higher the percentage. If you think about it, that does make a ton of sense, right? I mean, I think if you think it through, in other words, go to the limiting case. Like, the sine of 0 is 0. And remember that for the rest of your life, please. And the sine of 90 degrees is 1. That's like saying the sine of 0 is 0%. And the sine of 90 degrees is like 100%. What we're saying is, if you put a block on it, if you take a slide and you incline it at an angle of 0, if you just make it horizontal, things don't slide at all. They would accelerate down at 0% of 9.8. They won't fall down at all. But as you start making these slides steeper and steeper and steeper, things will begin to slide down it. They begin to accelerate. And the steeper you make the angle, the more they accelerate. Now, and they range in their acceleration all the way from 0 all the way to the limiting factor, which is if you made the plane fully vertical, if you made it 90 degrees, something would fall down at 100% of 9.8 meters per second squared. Would be free fall. Anything in between would be some percentage that gets bigger and bigger as the angle gets bigger. Like if you go to 30 degrees, the sine of 30 degrees is 1/2. So if you go to 30 degrees, things slide down at like half of 9.8 meters per second squared. They fall down at like 4.9 meters per second squared. If you go a little higher to 45 degrees, then the sine of 45 is like 0.707. So it's like 71% of 9.8, or, so like basically 7 meters per second squared. Then you go up to 60 degrees. It's like 86% of 9.8, etc. So one thing is, I want you to know, when things go down a plane, they accelerate at g times the sine of the angle of the plane's inclination. The greater the plane inclination, the greater percentage of free fall they fall down. I think that makes sense. And I think you can show that that's true. My argument here, and your task on the final exam, is you're going to show that that is true, whether you look at the situation through the natural instinctive coordinate system, for which the x-axis is parallel to the lab table and the y-axis is parallel to the wall, right? If you use that coordinate system, you do all the physics, you'll find that A equals G sine theta. But if you do it and you do it right, you'll find that you have to do a lot of math to get there. So it makes sense. The instinctive thing is just to go, okay, here's my coordinate system. I'm going to do math now. Then you end up having to do a lot of math. What I want you to also be able to show me is, if you use a physics insight, if you actually treat it like a physics problem, not just a raw math problem, and you say, Galileo gives me permission to apply the laws of physics in any unaccelerated coordinate system that I want. So I'm going to tilt the coordinate system like that. I'm going to line up the x-axis with the line of acceleration. Then even though that's a little bit funky to do, and even though you have to think, you end up breaking up different forces there, and you end up breaking up gravity, which takes a little bit of conceptual thought, but you end up doing a lot less mathematical computation to get the same answer. I'm not going to do the whole thing for you right here. Again, that's what I've been trying to show you for the last 3 days in class notes. I'm going to tell you again right now, in the class notes, we've been including all this friction. So what we've been doing in the class notes is actually harder than what I'm asking you to do. So in the class notes for the last 3 days, we've been doing a friction inclined plane, which all of those notes together. Oh, wait, okay, I see something good in the chat. I'm gonna look at that in 1 second. Great. I'm going to look at that in 1 second. Let me just finish this statement, but I'm glad things are happening in chat. You should be asking questions about this. As an overall thing, your class notes from class for like the last 3 days are pretty important to the final exam. What I'm actually trying to tell everybody is that you've got all this material from the last 3 days that really is dividing into two different problems on the exam. All the material was friction on an inclined plane. And I was trying to make 2 points for the last 3 days. One, the coordinate system choice matters. And two, up is different from down. It's going to be your job to sort of thread through that material. But I'm saying now, if you look, and I definitely appreciate the question that's in the direct chat. Just give me 1 second. I'm saying, if you look through that material, you will see that either way, no matter what coordinate system you're in, the system schema for a smooth inclined plane, like in the material, you've had friction. That makes it harder. If you can manage it with friction, you can definitely do this. If you take out the friction from the last 3 days, an inclined plane system schema is what's up in the top right here, and it's the same either way. The pure free body diagram is what's on the board right now. And it's the same no matter what coordinate system you choose. But then, if you look at that free body diagram, if you're following the physics of the last 3 days and of life, you'll realize, okay, one of those forces has to be broken up into components. In order to apply F net equals MA on an x-axis and a y-axis, I need an x-axis and a y-axis. I need both of those I need all forces to lie along axes. So you'll realize you've got to break up one of those forces. To know which one to break up, you have to choose what your x-axis and your y-axis are. I'm saying now that you're going to, on the final exam, you're going to make both choices, like one at a time. And you're going to show how the two different methods still arrive at the same place. But one method is a lot mathematically cleaner than the other. And that's why we do it. In other words, this is my last hint for now, and then I'm going to answer the direct chat question, and then I'm going to go on to another thing. I'm saying, and again, this is a summary, like, you'll see more explicitly in the document that I post, but I'm saying if you choose one coordinate system, if you choose a coordinate system where the y-axis is parallel to the walls and the x-axis is parallel to the floor of the lab, then you'll see that the normal force has to be broken up, and it'll be broken up according to this diagram. And that seems natural, but then you have to do F net equals MA on each axis. And you do have to. And you should practice without looking. And once you do F net equals MA on each axis, then you're going to have to do this algebraic substitution. Again, I've been doing it in class, but with class, it's even harder because I've been doing it with friction. Here, you don't even have to do friction. But you have to walk through the whole thing and ultimately solve for A. It's not easy. But if you break up the diagram the other way, if you tilt your head and break up MG, which is not an easy thing to think of, but if you do it, and then you apply F net equals MA to that, you'll have less work and you should get the same answer. So these are like proofs. It's not a mystery what the answer is. It's you want to practice these things and show yourself and show me that you see how to arrive at the same answer both different ways. You'll know you've done it right if that's what happens. And then you'll see why one way is actually more mathy and the other way is more physicsy. Okay, so that's question 2. I mean, I don't know what order the questions will be on the final, but so there's 2 questions on the final exam that are both very much about inclined planes. They're very abstract seeming until you get used to this stuff. But one is to compare up versus down on a rough inclined plane, and the other is to compare one coordinate system versus another coordinate system for a smooth inclined plane. That's what I'm saying so far. Now I have more to say. I mean, and I've got 25 minutes to say it, but there's definitely a good question in the direct chat or in the chat. In the chat, let me go. Hold on one second. Sorry. Oh, it is direct. I'm sorry. Oh, great. I'm sorry. This is a great question. I'm not going to read the person's name, obviously, but yes. So someone said yes. The angle affects how. Right. Great. This is a great question. Hopefully the person's saying that they didn't understand a certain thing before, but I'm thinking it sounds like they understand now. Yet I am saying the angle of an inclined plane affects how much of gravity actually sends the object along the inclined plane. Yes, I'm saying yes to the direct chat person, and there's only one direct chat person. So if you put something in direct chat, I am talking to you. I'm saying yes, the angle will affect how much of gravity will affect the object. And yes, to everybody, especially in this diagram, I'm totally talking about this diagram right here. I'm saying really that gravity pulls everything straight down. But when the whole thing about vector components are real. They're not just a mathematical abstraction. I'm saying gravity always, your weight pulls you straight down. But if we put you on a slide, if we put you or some object on an inclined plane, if you think about it now, gravity is pulling straight down. But on an inclined plane, straight down really means two different jobs at the same time. For the Earth to pull you straight down toward the center of the Earth is in one sense, is partly to pull you down along the plane. That's one job it's doing. That's one vector component, the component I'm calling mg sine theta. But it's also at the same time to pull you into the plane, against the plane. Like your weight is doing two things. It's keeping you on the plane to some extent, and it's sending you along the plane to some extent. The two vector components of mg sine theta and mg cosine theta, represent the two jobs that your weight is independently but simultaneously doing. The mg cosine theta is the job that's keeping you against the plane. It's being balanced by the normal force of the plane. And so ultimately it's affecting how much friction is rubbing against you from the plane. The mg cosine theta is how much your weight is keeping you on the plane. That's cosine theta. And if you notice, everybody, as angles get bigger, the cosine of an angle gets smaller, right? Sine makes sense to most of us, but cosine is kind of counterintuitive to most of us. That's how I remember it. Sine, sensible. Cosine, counterintuitive. Cosine of 0 is 1. Cosine of 90 is 0. That sounds crazy, right? And people can often not remember it, but it actually makes sense here if you think about it. The bigger the angle, the less gravity is keeping you on the plane. If the angle is 0, gravity, your weight is entirely keeping you on that slide. As the slide gets inclined more and more, gravity is keeping you less and less on it. The cosine component is going down. You're getting less and less friction from the plane. But to answer the direct chat person, the other component, mg sine theta, the amount that gravity is sending you along the plane is getting bigger and bigger. So yes, I am saying that, I mean, I hope this, I think it's great that the direct chat person put what he or she did. And in fact, maybe just acknowledge to me if I'm responding properly to what you're saying, please let me know. But yes, it sounds like at least one person in the room is now sort of seeing that mg sine theta is the portion of your weight that is sending you along the plane. And the steeper the angle, the more of your weight is doing that. The other portion of your weight is just keeping you against the plane. And the steeper the angle, the less your weight is doing that. Does that make sense, direct chat person? I don't know, but well, hopefully, oh great. All right, thank you. That's awesome. Awesome. Great question. Okay. So all right. So again, I'm going to post an actual, practice document for the final exam, but I'm just trying to take the surprise elements out of this. Also, secretly, what I'm trying to tell you all, why am I talking about this now? Why am I going to talk about it again in our last class? Is because I'm really trying to emphasize to you all, and a lot of you did realize this is this not about knowing answers. It's about, who's that? Oh, okay. Sorry. It's not about knowing answers. I'm trying to give you the answers in advance. It's about really proving why the answers are true and why you understand the answers. So what does that really mean? It means the more you can just practice. I don't need you to read you can read the book and stuff, but it's not about doing a million different problems to prepare for this final. It's about practicing the ones that you already know are going to be on it. Like, honestly, all of you practice. Try doing these problems without looking. Try a couple of times. Like, it's really about, the more you practice, the more it'll get in your bloodstream and you'll really see all these concepts in a much deeper way. Okay. So that's 2 problems on the exam. Now there's going to be one more problem. This is what I'm going to race through a little bit today. One more problem that'll cover these last final equations that I'm giving you right now. and Monday, I'm going to give you a couple final equations that will help you a lot sail into Physics 204. Again, anything I'm going to say now for the next 20 minutes about sort of new equations, I mean, and some of them you sort of seen in Lab 6, but anything I say now and I repeat on Monday, like anything I say now, you'll see in the practice document. I'll repeat or expand on Monday, and you'll only be asked to the level of difficulty that you see in the practice document. In other words, I'm aware that I'm saying some things now that I'm only going to say for a short amount of time. So I'm not going to ask very elaborate questions about them, but I want them to be in your synapses before next semester. So there are a couple last force equations that I'm going to give you. One, and that's, so the last problem in the exam, we'll deal with these. Okay, so part A. What if we have a spring? What if we take a metal coil and we attach one end of it to a wall and we attach the other end of it to some mass, okay? Springs exert forces. I want to talk about we've talked about the force exerted by surfaces pushing against each other. We call it friction. We call it normal. We've talked about the forces that are exerted by strings, and we call that tension. We've talked about the force of mg, your weight. I want to introduce briefly another kind of force, the force that's exerted by a spring. So what's the deal with, or anything elastic? What's the deal with elasticity? Like, what does it do? How does it work? Why is it special? It works like this. If you have some horizontal spring, there is a place that the edge of the spring would like to be in general, a place where if you put the edge of the spring there, it'll stay there and it won't move away from it. And if you try to put the edge of the spring somewhere else and you let it go, it tends to start moving toward that preferred position. That preferred, or that more stable stationary position, is called equilibrium, right? Springs have, the edge of all springs like to sit in some orientation that we call the equilibrium orientation. Wherever the edge of the spring is, when it just sits there, normally when no one's doing anything to it, we call the equilibrium position. And we designate that x equals 0. Wherever the edge of the spring sits when you don't do anything to it, that's called the equilibrium position. If we pull a spring to some other, if we put a mass on the edge of a spring, and like assume that one edge of the spring is fixed to the wall, and now we start playing with the other edge. We put a mass on the edge of the spring and we pull it to some other position where x doesn't equal 0. Whoop, sorry. Like where we just call some position x naught, not right. So some position x naught, not 0, but just some position x naught. If we hold a mass at some position x naught, we feel a tug from the spring. We know in order to keep the mass sitting there at x naught, we got to keep holding on to it. We know from life experience that if we let the mass go, it's going to be pulled in toward x equals 0, right? So we know that springs exert forces on masses, and they exert forces on masses that directs the mass toward the equilibrium position. Like even on the other side, if we were to push, if this is a good spring, and we were to push it in, compress it, and try to hold a mass somewhere to the left or on the negative side of the equilibrium position, we know there too, we'd have to keep holding it in order for it to stay there. If we let it go, the spring will push it back toward equilibrium, right? So springs exert forces, and we call them restoring force. A spring exerts a force that we call a restoring force. We call it restoring because it seems to always try to send the mass back toward an equilibrium position. Specifically, if you hold the mass on the positive side of equilibrium, the force seems to always be directed in the negative direction. If you hold the mass on the negative side, the force seems to be directed in the positive direction. So the force exerted by the spring always seems to be opposite to wherever the mass is displaced from equilibrium. That's number one. That's direction. Magnitude-wise, I'm saying if the mass is at position 0, the spring doesn't exert a force at all. When the mass is at equilibrium, that's equilibrium. There's no force exerted by the spring. The net force on the mass is 0. The acceleration is 0. But when you put the mass anywhere that isn't equilibrium, then the spring seems to exert a force. Well, the force can't just pop out of nowhere. It's not like a cartoon. If there was no force when the mass was at zero, but then there is some force when the mass is at non-zero, the force exerted by the spring must grow continuously from the value of zero to something else. Like it can't just pop. It's not a step function. It must be some sort of continuous function. And in fact, you know from experience, if you've ever gone to a gym, which clearly I have not, but if you've ever like played with exercise equipment or whatever they are, gym equipment, right? If you think about it, a lot of gym equipment and exercise equipment is made of springs, big springs or small springs or lots of springs or something. They rely heavily on the concept of elasticity because they give you this phenomenon where in order to hold, if something's held together by springs, in order to hold it here, it might take a certain amount of strength on your part just to hold it there. But to hold it out here takes even more strength, right? To hold it where it wants to be held and relaxed doesn't take anything at all. But in other words, I'm arguing the more a spring is stretched away from equilibrium, apparently the greater the force is exerted by that spring. It's zero when it's zero. The force is zero when the displacement is zero. And as the displacement that we ask of the spring grows, the restoring force of the spring grows. The force seems to be related to or proportional to the displacement from equilibrium. This is the nature of elasticity. An elastic force is a force that is proportional to displacement, to position. And I'm going to turn the page in 1 second, but that's the new exotic thing. Some forces in life, such as the elastic force, actually change. They actually vary as a function of position. The forces we've been dealing with up until now have not, but the elastic force does. The good news is, to a good degree of approximation, under fairly controlled conditions, as long as your spring is long enough and the displacement that you're asking of it is comparatively short enough, it turns out that the force is not just proportional to displacement, but it turns out it's roughly directly proportional. The good news is that if I made a graph of force as a function of position, the good news is that that graph is a straight line graph. So it's not craziness. What I'm saying here is if I were to make a graph of displacement from equilibrium on some spring, call that X, and I put that on the horizontal axis, and on the independent variable axis. And if I were to plot force on the dependent variable axis, F, force as a function of displacement yields a straight line graph with with a y-intercept of 0. It's a straight line graph, constant slope graph. It's in the fourth quadrant because, as I was saying before, the force is always in the opposite direction of displacement. So if you pull the mass to the right, the force pulls to the left toward equilibrium. Also, the graph continues too, I should say. Sorry. If you were to pull the graph, if you were to pull the mass to the left, then the force would pull to the right. So the graph goes on forever, but it's a straight line direct proportionality. Force is linearly dependent on displacement. That means the slope of this graph is constant. The rise over run is a constant. That constant, the rise over run, the amount of newtons of force the spring exerts for every meter of displacement from spring equilibrium, that constant slope, that constant ratio, that constant rise in force per run in displacement is ultimately known as K. K is how strong a spring is. That's what it's trying to say over here. Not K. K. Well, K is very strong and very strong student. It was a gorgeous exam, I might add. But sorry. But the gorgeous exam, I said. Not anyway. But K in this case, the letter K represents. Sweet. I'm glad you heard that. Okay. Cool. Okay. Sweet. And I do mean it. Okay. Sorry, I totally distracted myself. They hadn't invented ADHD when I was born. So yeah. How many light bulbs does it take to screw a physics professor? Okay. What? Okay, so K is the stiffness of the spring, the strongness, the strength of the spring, meaning K is a constant ratio of how many newtons of force is exerted by the spring for each meter of displacement that you subject the spring to. So one spring might have a K of 300 newtons per meter. That would mean that it's 3 times as strong as some other spring that has a K of 100 newtons per meter. It means that you put both the springs down. If you try to stretch each one a meter out from its equilibrium, the stronger spring pulls back with a force of 300 newtons for each one of those meters. If you try to pull it out to 2 meters of displacement, it'll exert a force of 600 newtons, whereas the other one, right? So K is the ratio of force per unit length. And the higher that ratio, the stronger or the stiffer the spring is. Ultimately, all reasonable springs are described by this law at the bottom, this equation called Hooke's law, F equals negative Kx. Okay, that's one big takeaway of what I'm saying right now. I want you to know Hooke's law for a spring is F equals negative Kx. It's another equation. It's like saying friction is mu times the normal. When I say it's another force function, I want to be clear that this does not contradict or replace Newton's second law. Newton's second law still says, Newton's second law still says that the sum of all forces acting on an object divided by the mass of that object produces the acceleration of that object. This Hooke's law is just what the equation for one more force that could go into a free body diagram and could be inserted along with others into the left side of F net equals ma. You see what I'm saying? Like, it doesn't contradict F net equals ma. It's just another force that could contribute to overall acceleration of an object. But this force is the force exerted by a spring. It's Hooke's law. It's F equals negative Kx. And we have 8 minutes left. I'm totally watching. The one more thing that I want to say, though, so this is like part A. I will not ask you hard questions about this, largely plug and chug or something, but I want you to know that this is another force to know about, and it could go into a free body diagram or whatever else. And Newton's third law applies to it, everything else. But so that's part A. Then part B, I want to say now, and I will warn you that there's a part C, and that I'm saving for Monday. There's a part C of this third question. I'm saving that for Monday, but that's it for the whole exam, okay? So your whole exam is like 3 problems. 2 of them I just discussed at the beginning here. One has 3 small parts. 2 of the parts I'm getting to right now, and one part C. If you see it in the practice document tomorrow night, you won't recognize it necessarily, but that's what I will clarify and expand on Monday in our last class. And any other questions you ask about the final exam, we'll answer. Okay, so just to be clear, so the final exam is like 3 problems. One of them is 3 parts. So here's part B of it. Part B, notice F equals negative Kx. This elastic force, this Hooke's law, this spring force, varies continuously as a function of position. Like I mentioned a moment ago, part of the reason we care about this force is because it's a variable force. Unlike mg, for example, like mg is your weight. Your weight is your weight approximately, like whether you're 3 meters above the ground or 4 meters above the ground, nobody cares at this point in the class. The force pulling you toward the ground by the center of the earth is just mg. It's just a constant number. The spring force is not a constant number. It varies from position to position. And there are other forces like that in nature and in the world, and that we get into in physics 204 and stuff like that. Forces can do that. So how does physics deal with forces that actually change in magnitude from position in space to position in space? We have a technique in physics that you did come across in lab 6. Not going to ask a lot of questions about lab 6, but now you're going to see right now like why you even did lab 6 or what it was about. What you find in physics is there's this idea that we discover or we construct or we define. There's this idea called work that we come up with in order ultimately to deal with forces that vary over intervals of space. in order to deal with forces that do different things as you move through a space, we invent or discover this idea called work. And work is the amount of work is force times displacement, to put it in simple terms. I mean, that's what it says at the bottom of the sheet here. If W stands for work, ultimately work, the work done by one object on another object, is the force exerted by one object on another object times the displacement that the object is moved through. So if I exert 1 Newton of force on a box while moving it through 1 meter of displacement, we say that the total effect of my force, the total consequence or impact of my force acting throughout that whole interval of space, the accomplishment of my force in achieving, in succeeding in moving, displacing this mass throughout an interval of space. If I push with 1 Newton of force in order to get something to move 1 full meter of displacement, we would say that I did 1 joule of work on that object. A joule in physics is a joule of work is a Newton of force times a meter of displacement. And there's more to be said about this, of course. And yes, this is the same joule that you might remember from chemistry, as in 4.18 of these things equals a calorie. Yes, it's all related in the end. In the end of the day, when we do work on things, what we accomplish is we transfer something that we ultimately call energy. And indeed, energy is measured in the same unit as that work is measured in, not coincidentally. And that unit is called a joule. But what I want you to know just for the moment is that when you exert a force through some displacement, you accomplish something that we call work. And technically, and I have 3 minutes, I might even finish 1 minute early. You see this triple equal sign. I'm defining work to be force times displacement, but there's one technicality here. There's actually a couple of technicalities, but there's one technicality I want you to be aware of before we end today. And we have our last class on Monday. And that is, I'm putting little triangles before the W and before the X. I'm putting a little triangle there, a little delta. And that's the same delta that you use in math to mean difference, right? Like as in delta Y, as in rise over run, delta Y over delta X. And when you put the delta in Y, you mean like Y2 minus Y1 over Y, X2 minus X1. Delta is used in math and physics to mean difference, specifically to mean small but finite difference between 2 values of a variable. That's what delta means, a difference, a finite difference between 2 values of a variable. So technically, I just want to say right here that technically what I'm defining is a small amount of work that's being achieved in a small amount of displacement. If you move something from one position, if you move something throughout a small but finite difference between 2 positions, then the force exerted through that small but finite displacement yields a small but finite amount of work. I have to have this technicality here and leave you with this technicality. I have to say that when I'm defining work right now, I'm defining it for a small but finite displacement. And a very reasonable question with 1 minute left that you might ask is like, well, first of all, why are you saying that? Yeah, but more to the point, you might say, what do you mean by small? How small is small? By small, I mean a displacement that's small enough that we could know what F is for it. A displacement that's small enough that F doesn't have too much room to vary yet. In other words, as long as this displacement is small enough that you know that it's 3 newtons of force, then you multiply 3 newtons of force by that displacement and you'll get the work for that displacement. The thing this doesn't tell us yet is what to do when the displacement gets big enough to allow that F to start changing. Like that's a discussion for another time. But what I need you to know right now is as long as the displacement is small enough to allow for some number F, then the F times the displacement equals the work And that's it. And I see people leaving, right? And that's, so you've been great. I'll see you one more time. I will post things. I will get things back to those of you that I haven't. You'll get things to me. I apologize. I love you dearly in a professional way. And have a great weekend. And yes, have a good day.
Professor?
Yes.
Hello? Can you hear me?
Yes, let me just turn off some.